So, we will continue with this module on embedded passives technology. It is also known as embedded components technology. So, this is going to be a very important technology in the current few years from now on, because this is a growing technology and there are still many groups that are working with embedded passives. And as far as industry is concerned, as I have mentioned in the last lecture, people are still working with new designs on how to create embedded passives, that is embedded resistors, embedded capacitors and embedded inductors into their design. Ultimately, the fruit of these exercises is to get a printed wiring board, a system level printed wiring board that is highly miniaturized, that has got very high density in terms of components. At the same time, we are also looking at how best the electrical performance and thermal management issues are being taken care of when we use or employ embedded passives. So, what I will right now do is take you into a quick recap of what we have seen in the last class in this embedded passive components technology. All of you were and are familiar with plated through hole components, that is, you have resistors that have leads, right, and these can get into a system level printed wiring board. Then we talked about surface mount devices. Typically, if you have the surface of the board here, then you will have these passive devices mounted on the surface of the board. Okay. So, the soldering methodologies for plated through hole component and surface mount devices are different. We have seen that. So, the issue is soldering problems and reliability issues associated with each of these technologies. Now, we are talking about embedded components, that is R, C and L, which means if you have a system level printed wiring board and then if you have a core of the printed wiring board designated, you can embed R into one of the layers and C and L respectively and connect them to the copper interconnects through micro vias, right. So, the key to this technology is what kind of geometries or feature sizes you can work with in embedded resistors, capacitors and inductors, how they can improve in the production or fabrication of high density, high performance system level printed wiring boards. Then we talked about resistors, embedded resistors, and we have seen the key issues for working with embedded resistors. That is, the design is a major issue. Then we talked about fabrication issues. Then the other points that are of due importance for resistors are the electrical test, that is the electrical test and reliability issues. So, in terms of resistors and capacitors, we are going to see embedded capacitors in a bit from now. What we have seen in the last lecture is the design library for resistors, how the resistors patterns are generated, how you can create them and maintain your own library in your CAD system. As I mentioned in the last class, that there are no set standards as far as library modules in the CAD system for resistors and capacitors embedded. So, you as a designer need to know how well you can exploit your design knowledge into integrating these devices to fabrication of these devices into the system level printed wiring board compatible format. So, that is what we saw in the last class, the different methods of fabrication of resistors. As you can recollect, you can fabricate resistors by polymer thick film or PTF as you can call it. Then the second one is the foil method, how you can laminate resistor foils with the printed wiring board dielectric material, and finally, electroless plating as a key methodology to plate resistor materials like nichrome or nickel tungsten phosphorus and so on. So, we have also seen the materials used in each of these methods to create embedded passives. Now, the other important issue is that if you embedded resistors, you are able to integrate it into a system on package format, okay, which is the current technology today to miniaturize system level printed wiring boards. And we also talked about system level integrated module based on organic substrates. I do not have to emphasize here that organic substrates are very cost effective, okay, and you have to always look at building embedded passives in an organic substrate. Now, if you recall, I also talked about hybrid circuits in the last class, where hybrids technology has been known much earlier, and especially the thick film circuits talked about screen printing thick films of resistors, copper conductive based or capacitors or inductors, and then co-firing them using LTCC process or HTCC process, and then realizing modules including multi-chip modules. So, with this background, we will continue with today's class. I will just borrow this slide once again from the previous lecture to highlight again the importance of embedded passives and to help you recollect. The highlight is it improves the packaging efficiency, there is no doubt about it, provided you provide a high end design that is manufacturable, that is testable, and that is reliable. Just now I talked about SOP slim integration. Then we have to aim at reducing the size of the components. It eliminates the substrate assembly altogether. So, if you have, for example, 100% embedded passives or 95% embedded passives in your design, you can do away with most of the soldering or joining methods, and thereby reducing the risk of failure arising out of solder joints, minimizing solder joint failure and enhancing reliability. Then in terms of electrical performance, it can be faster and cleaner, adding functionality to the board, and then more design flexibility in terms of tolerances and values. Although on the negative part of why we need not go into embedded passives is that more and more surface mount devices are available in lower profiles or formats. And the important key issue is it is lead free. Now, the challenges that we face with the embedded resistor process, firstly, you must understand the PWB process technology to work with embedded resistors, because invariably you have to work with organic buildup. So, basically first is, as a designer, please understand what a PWB process sequences are, and in terms of the high density interconnect technologies, what are the build up technologies that can be used, and to enhance performance, what are the various dielectrics that are being used in the build up of the high density interconnect, because you can take advantage of nicely integrating the resistor process with these technologies. So, the challenge firstly is how can you maintain the resistor tolerance as compared to devices that are available in the market today with specific values and specific tolerances that are mentioned. So, when we say tolerances in terms of resistances, can you fabricate a material with 1% tolerance or 5% tolerance or 10% tolerance that is acceptable in your product is the key question before a designer. And this has to be translated into discussions with the manufacturer who can manufacture embedded resistors. So, both resistivity, when we say resistivity, it is the sheet resistivity. So, typically what kind of materials are you going to use? Is it going to be 10 ohms per square or 100 ohms per square, or is it 1k ohms per square, or are you going to use a set of different materials for different layers to achieve a range of resistances that are required for your design. So, in terms of challenge currently, as far as embedded resistors are concerned, these two are very important. Sheet resistivity in terms of choosing the right material and the process. Can you get a specific set of resistor values using polymer thick film? Can you get it by electroless plating? These are the issues that need to be discussed with your manufacturer, and the goals which have not been met by resistor materials suitable for resistivity required for widespread applications. So, basically you have to look at applications and then accordingly decide on your design. Then as far as the manufacturing aspects are concerned, yield is a major issue. Okay. When you work with surface mount devices or plated through hole components, you should be prepared to replace and repair these devices if they end up with failures, but here repairing is going to be very difficult. So, because embedded resistors in some sense cannot be repaired at all if the inner layers containing the resistors are built and sequentially laminated with your signal layers. So, yield loss per device must be extremely small, okay, because the repairing part of it is very, very remote in the case of embedded resistors. Cost wise, cost is an issue that is influenced by the kind of materials that you use in embedded resistors. So, the process should be cost effective, cheap enough to reduce the overall cost. Okay. So, are you going to look at a more cost effective polymer thick film process, or is it going to be a foil method which could be slightly expensive compared to a polymer thick film process, or more precise in terms of thickness, electroless plating. Okay. So, that depends on the material, that depends on the resistor range that you are going to work with, and how you can employ these methodologies suitable for a particular customer in terms of whether it is a medium dense board, high dense board, and so on. So, remember, three challenges still exist today for embedded resistors. One is the resistor tolerance and sheet resistivity, interrelated, yield issues as far as production is concerned, cost effectiveness, and finally, I would like to add here one more important point, which is your understanding of the design library. Okay, how effectively you can build a design library, understanding your knowledge with process issues translated back to creating geometries that could effectively be used for future designs. Now, we will move into the next topic in embedded passive components, that is embedded capacitors. What are the types of embedded capacitors that can be designed, fabricated and tested? The first one is singulated capacitors, and the second one is distributed capacitors. What are the types of materials that could be used? Inorganic materials and organic materials. Now, unlike resistors, capacitors need to be understood in a much better fashion, because the applications are varied, the requirements are also varied, and you also have a host of materials that you can employ to realize capacitors. As you know, in the plated through hole capacitors, the materials are fabricated by thick film technology, okay, and the same is the case with SMD capacitors. So, they are actually co-fired and trimmed to the required tolerances that you require, and then the good part of using these devices are that today you have equipments that can handle miniaturized surface mount capacitors. So, how do we go about working with embedded capacitors when there is already a challenge in terms of availability of low formats or small formats of SMD devices, especially 01005 or 0201 is already a well known standard. Now, let us have a look at some of the basis for designing embedded capacitors and inductors. We will not deal with too much of inductors in this particular lecture, rather we will focus more on capacitors, but the technology of creating each of these is very similar. So, that is the reason why I brought this illustration here in this particular slide. So, the embedded capacitor technology is based typically on the well known equation, all of you are aware of this. Capacitance is related to the dielectric constant of the material and the area of the capacitor material and then the thickness. So, typically you have a sandwich structure like this, where you have the metal plate, then here again you have a metal plate, and then in between you have the dielectric material of specific dielectric constant. Okay. So, d, the thickness of this is a key component in deciding the capacitance, and then you also have the area of the material. So, area of the conductor material, the thickness of the dielectric and the volume of the material used as the capacitor material and the sandwich structure, and based on this equation you can play around with creating different geometries that can provide different values of capacitances. Similarly, inductors can be created on printed wiring board substrates. Typically, you can create different geometries, spiral and so on, bar type or meandering type of inductors. Okay. And these can be simply created by a print and etch method of the design that you require. So, embedded resistors, capacitors and inductors can be judiciously employed in your PWB design itself. So, we will slightly dig deep into the factors deciding the values of the capacitors. Dielectric constant is very important. It is an intrinsic material property that represents how well a capacitor stores charge when a voltage is applied along the area of the material. Although it is called the dielectric constant, the value changes based on many parameters such as temperature, the frequency of operation, voltage applied, and time of interaction. So, as seen in this equation above, the dielectric constant, high dielectric constant results in higher capacitances. So, if you want to have, for example, using a sequential build up technology and employ different embedded capacitor in the build up, one above the core and one below the core, you can very judiciously use different capacitor materials to get different ranges of values, one at the top and one at the bottom interconnected, and these capacitors can be interconnected to the signal layers, the ground planes, and to the core by micro Vs. So, that is the advantage of using embedded technology. So, for this reason, higher dielectric constant materials are desired in certain applications where space is limited. So, the use of embedded capacitors will be highlighted if you can work with smaller geometries and reduce the size overall or the profile of these capacitors, and the area of these capacitors can be reduced in the entire build up to such a extent where it will be high performance, high dielectric constant materials being used in these cases. Now, the other issue what I am showing up is how you can build a design library similar to the resistors that we talked about. We talked about how resistor library can be built by using bar type resistors or meandering type resistor shapes and geometries. Here, in the case of capacitors, what we have demonstrated here is basically to show you a set of geometries that could be utilized in creating capacitors. Here you have a circular geometry, a square, and you can also see there is a micro via interconnect that could be seen here. So, basically you are looking at a metal layer and then a sandwich material, which is the dielectric that we are talking about, and then again the other copper layer. So, these kind of structures can be created on your printed wiring board. Choose the right appropriate dielectric constant for this thickness of dielectric that you intend, and then you can interconnect them using micro Vs. So, as you can see, this is the top layer of the design. If I can go back, you can see this is the bottom plate. Then in the build up you will have a dielectric material at overlapping these particular structures, and then you will have a foil or added copper to the dielectric material, and these will be interconnected through micro Vs for testing. So, these geometries will behave as a capacitor. Now, the area is very important, and then the value of the dielectric constant in terms of the material used is also important. So, this is the test board that you are seeing here demonstrating series and parallel capacitances for various geometries, and then these kind of geometries can be explored for your design. Now, briefly we will look at the process details for embedded capacitors. So, I am not going to spend too much time on how such designs can be created. Just as we talked about in resistors, it is up to the designer to play around with the knowledge of the material available in the process and then decide on the geometry that you require. So, the key here is the takeaway from the previous slide is that decide on geometries that can best fit with lower area occupied in the printed wiring board, but it should be possible to produce high capacitances with high dielectric constant materials. Firstly, in terms of process, we could have inorganic methods, okay. Typically sputtering using chemical vapor deposition, thin film deposition practiced in microelectronics industry. So, it could be easily adopted into the fabrication methodology. Ideally, these are suited for small areas, not really suited for large area fabrication that you would see in the printed wiring board arena. Then the second one is the sol gel method, where you can deposit a thin film of high dielectric constant material, okay, using sol gel methodology that is well known in the materials field. And there are different materials that could be used. It could be, for example, lead, lanthanum, zirconium, titanate, ferroelectric material. Today in this field, we have seen the use of ferroelectric materials and paraelectric materials that exhibit different properties based on the crystal structure. Then the other method is anodization, that is very typical of aluminum, vacuum deposition of aluminum and tantalum to form thin dielectric oxide layers that can produce capacitance values based on your requirement. So, these are the inorganic methods. Again, very good for prototyping, very good for small area products. But the one important thing that we have to talk about is this really suited for large area manufacturing, and cost is an issue. So, large area and cost are definitely issues that might weigh down against the inorganic methods. The other one that is kind of more familiar with many of the manufacturing industry is that the use of polymers and the use of polymer ceramic method technologies, where you can, for example, if I can focus on the polymer ceramic method, which is known as the mixed method. So, you take a polymer as a media, okay, and then take these ceramic powders with the specific dielectric constants, and then you can mix them together to get a very good homogeneous mixture, and these can be applied by, let us say, spin coating, typically more in favor of spin coating and other coating methodologies to an organic substrate, okay, that contains the bottom plate, typically copper, of a printed wiring board, and then on this polymer ceramic cured material, you can either laminate a foil, a capacitor foil, or you can deposit copper by electroless plating followed by electroplating methodologies. So, this looks very familiar and looks like highly high possibility of integrating with the printed wiring board technologies. Now, we will talk about using organic polymers. Now, the advantage of this method is simple ways of mixing and dispersing the material, but has low permittivity, otherwise it is an ideal choice, like polyvinylidene fluoride, PVC, polypyroles, etc. Improved safety factor due to suppression of combustion and low equivalent series resistance values. So, using polymers could be a solution in terms of large area manufacturing, but if you want to synthesize your own capacitor, the polymer ceramic method is a highly advantageous method, because you know the dielectric constant of the polymer material that you are using, and then you can also formulate ceramic powders based on the dielectric constant, and then your design that requires these values. And then the key issue here is the mixing to get a homogeneous mixture, a good dispersion of the ceramic powders. Now, you could also use nanomaterials to make it as a nano composite formulations synthesis, and then this could create very high, you could establish very high capacitance values for high performance printed wiring boards. Now, what I have given here is a list of materials in terms of substrates and the capacitor materials that could be used in this industry. So, the issues here are dielectric constant, important factor, dissipation factor, and TCC, temperature coefficient of capacitance. So, Teflon, you can see the values of dielectric constant, benzocyclo butene 2.7, polycarbonates, silica, epoxy is well known in the PCB industry, and then we have this alumina powder, tantalum oxide, barium titanate, much used in the capacitor industry. There could be other composite materials or inclusions in barium titanate, like strontium could be added. So, barium strontium titanate, so that you can synthesize or vary the properties by adding new elements. So, the wide range of capacitances from 1 picofarad to many microfarads is needed for various applications. So, you have to dig into various substrate materials and the binding material, as well as your the oxides that you require, to the filler material that you require to vary the property to suit your applications. Now, filtering and termination capacitors typically require low capacitance of 1 picofarad to 200 picofarads. So, accordingly you can synthesize. Then for decoupling and energy storage, the range of capacitances vary from a few nanofarads to few microfarads. So, with trial and error you can in fact vary the properties by varying material usage. Now, I will step into illustration of embedded capacitors that could be prototyped, and this could also be used for large area. Now, you take a bare board, this is a typical printed wiring board with the bottom electrode. So, this is the copper, okay, and this is typically could be your FR4 material, glass, epoxy, composite material. Now, you can typically do a subtractive process to get these patterns. Okay. So, this is the bottom plate copper, and typically you can do print and etch method. So, by using photolithography, then do a spin coating of the polymer ceramic nanocomposite material. You can see here in pink shade, this is the polymer ceramic material. Okay. You could also use a nano powders here. The key here is the right choice in terms of volume of the media, the binding media, and then the ceramic powders. Okay. So, there should be good flow, it should be easily used in methods like spin coating, and I want to emphasize here that spin coating for areas like 12 inches by 12 inches seem very ideal, okay, and you can get a very uniform thickness. So, thickness at this stage is very important. So, if you talk about different areas on the board, you would like to have equal thicknesses on the board. Now, typically spin coating by setting the properties of the spin coating equipment, you can get very even thicknesses across the board. Then you can laminate a copper foil after this is soft cured. Now, you cannot do a full cure because you need to laminate a copper foil. Okay. So, you can work with temperatures and pressures that are suitable for this kind of a system, and then use a copper foil. The thickness again is determined based on your design. It could be 8 microns or 18 microns depending upon your design requirement, and it also depends on the thickness that you have taken for the bottom plate of copper. Then it is now processed. Okay. Now, you have to realize a design like this that you see in picture F. So, for that you can go ahead with photolithography. which you are now familiar with in the PCB process. So, you can see that this process is highly integrated with the PWB process. So, you can laminate a photoresist, you can use typically a wet film or a dry film photoresist material, and then this now goes for exposure to UV light using a mask. So, let me write here that a suitable mask is very important. The mask defines the capacitor pattern. Okay. So, now using a right mask, you expose and develop to pattern the photoresist using a suitable developer, and then once you remove the photoresist after the allied processes in between, you will now get a sandwich pattern of the two metal plates with the capacitor material in between. So, what you have seen here in the picture is typical as a result of this process of using PWB methodology, photolithography, using FR4 substrate and a simple mask containing the capacitor patterns used for patterning your top and bottom plates of the capacitor. Now, let me recap. When you build these kind of structures, definitely you require to test them. You require to test these capacitors before it is actually sent to the next process stage. So, even in your design, you would like to connect your capacitors to other layers, as I said before, and for that you require to generate micro vias. So, let us see how do you integrate micro via process with the capacitor process. Okay. So, you can see here that this particular slide here shows a capacitor material and a resistor material that has been generated or formed on an FR4 substrate. Then apply liquid epoxy photoresist, right, and then expose and develop the via holes and fully cure it. Now, you have to interconnect these via holes or make it conductive by means of first electroless copper plating, okay, then laminating again the photoresist, exposing and developing the photoresist and with a soft cure process. Then finally, you can build the thickness of copper by using electroplating copper. Then strip off the required the photoresist that is not required at this stage, because all the patterning is complete. Now, you micro etch, remove the unwanted copper and then fully cure the board. Okay. So, this will result in the microvia connections for subsequent layers. So, you can highly integrate this particular embedded resistor and capacitor process with the SBU technologies that I talked about in one of the earlier modules, that is the PWB technology module. So, anywhere on the board you can design R, you can design C, you can create microvias and you can connect them to signal planes or your ground planes and your active devices. So, we are talking here about microvias of the order of 75 microns to 150 microns. Okay. So, these structures are very essential and you need to have very good resist material that can be used. For example, this step is very crucial, okay, to create microvia structures, followed by a very crucial step of electroless plating and then the build up thickness by electroplating process. Now, in the entire process, the previous process of fabrication and this particular step, I would like to mention a very key issue. The issue is addition of the dielectric material with the copper is a key issue in terms of reliability. So, at every stage, whether it is embedded resistor formation or capacitor formation, please have a look at the peel strength issues that always is related to reliability between the dielectric material and the copper. So, addition is also very key in terms of micro VIA reliability, because if there is a change in property during thermal cycling of the dielectric material, okay, if there is a shrinkage of the material, then the entire structure, micro VIA structure, will cave in, resulting in failure. So, this is a picture of embedded capacitors that have been successfully fabricated in CEDT using various geometries, using FR4 as a substrate, and you can see the test points for this particular test board and the micro VIA, or you can also generate initially plated through hole interconnects, okay, for testing. Now, this is a complete test vehicle picture that you are seeing on a organic substrate. The key here is organic substrate. Typically, you want to use high TG organic substrate, okay, with embedded R and C. You can see these are all capacitors, you can see resistors by polymer thick film method, and this is the pattern for ESD, electrostatic discharge testing. And you can also have a look at the micro VIA structures. Here in the capacitor, you can see the micro VIA structure suitable for testing your capacitors and interconnecting them. Now, as in any process, you have to do characterization of resistors and capacitors. So, some of the important points I would like to mention here is, look at the addition test. I mentioned before, copper and dielectric to be checked. Look at dielectric shrinkage, it should be minimal. Do thermal cycling, typically 125 C for 100 hours, less than 10% change in R and C values is expected, okay, to define tolerances and reliability. Temperature humidity cycling normally is done in the industry for new designs. So, less than 5% failures, it could be more rigorous with the industry, like less than 1%. Peel strength, in the case of resistors, nichrome foil and nickel phosphorus electrolysis deposits, again very key, because after building up you cannot repair these devices. And these typically here talks about the structures, then the range of values that you get for various structures in terms of dimensions and so on. And these are for the capacitors, okay, product A and product B, different thicknesses, and then you can look at the geometry, area, and the values that are obtained. And these results are in picofarads, and this is in ohms. So, normally the reliability is a very key issue, especially the thermal reliability and electrical test. So, whenever such a structure is built, we need to do a thermal stability test by doing a thermal cycling, and here you can see the results of temperature humidity cycling, and these are the results of thermal cycling of resistors by foil and electrolysis methods. And then as far as capacitance are concerned, you have to extract the capacitance using appropriate equipment. You can do a high frequency measurement and look at the adaptability of these structures for such applications. Now, these are some illustrations of various samples, inductors, capacitors by foil, capacitors by print and etch method, okay, resistors on a flex epoxy base. These are resistors by polymer thick film, and this is the cross section of a micro VIA that is highly recommended for high density interconnect structures using R and C embedded. And these are combined R and C board. This is the inner layer of a resistor that will subsequently be used for build up. And here you can see on the right side, these are assembled prototypes. What I am trying to show here is a working prototype of a product, a design using embedded R and C. So, it has been demonstrated in CDT by taking a particular design and kind of re-engineering by modifying the designs, especially replacing the normal resistors and capacitors with these structures and demonstrating the working of such kind of a product. So, you can see here a close up of a functional board with embedded resistors. In this particular case, you can see capacitors are mounted, there are active devices, there are other large through hole components also, but all of the resistors have been embedded into the one of the inner layers. Now, you can see here this functional board, this is with embedded capacitors. You can see here the inner layers, that is capacitor, and this is basically a small circuitry demonstrating the working of these embedded capacitors. Now, the idea is from this picture, if you are using a high end design, a manufacturable industry design, the geometries of these capacitors have to be reduced to such an extent that you can reduce the real estate of the entire board. And here you can see a prototype with embedded C here, and then these are embedded resistors. This is you can see in the background. So, the top copper layer has been built over the inner capacitor and resistor layers. So, this is a working prototype board. So, a case study has been done on a simple demonstration of the effect of using R and C on PWB miniaturization. What we have basically done is taken a standard double sided board, number of layers is 2, through hole technology, line widths are fairly large, okay, through hole via fairly large, the board size you can see 75 square inches. Then we try to move into the next step using through hole and surface mount devices, again 2 layer board, and you can see that the area of the board has been reduced. So, the board area savings is 60%. Now, it has been fabricated as a multi-layer, the same circuit, 4 layers, mixed component type, through hole and SMD. Then you can see the reduction in the line widths, micro vias have been used, some through holes have been used, and then you can see the reduction in the total area of the board with the board area savings around 75%. Then multi-layer built on both sides, embedded resistors 2 layers and signal in 4 layers of the 6 layer board. About 100 embedded resistors were used on the 2 layers of the embedded resistor layers. You can see the line widths used, micro via size is 100 micron, stacked via technology, and you can see the savings 82%. And then again a variation in that is that a 4 layer multi-layer board built up on only one side, signal layers 3, embedded layers 1, a slight reduction in the line widths of the conductors, same embedded resistors, and then you can see that we are able to show and demonstrate miniaturization using R and C. So, it could be cost effective if we can reduce the area and the volumes of the materials that are used, and the key here is the line widths that can be generated and the micro via sizes that could be generated. So, line definition and photolithography is definitely a key issue here. So, the conclusion on this particular chapter is that as far as embedded R and C is concerned, microvia interconnects and sequential build up technology are very key to build high density packaging at the board level, and you have to integrate them with embedded passive technology. Okay. And you can be cost effective only if you work on organic substrates. It enables SOP as we have seen. It can be fabricated by 3 methods: PTF, foil and electroless technology. Capacitors can be fabricated by foil and polymer nanocomposite, merges well with PWB fabrication process. eliminates through hole technology and surface mount devices. Although SMT is still highly popular, that technology is going to exist definitely for the next 5 years based on the kind of equipments that we are seeing, and it is highly popular. We are not going to see a radical change, although embedded passives are slowly getting into the thoughts of many industry people. Lead free is possible with embedded RNC. No standard design library is available. Laser trim of resistors is possible. Basic concerns are adhesion, peel strength, which you have to take care, and cost effective epoxy substrates and interlayer dielectrics have to be used, and you have to look at tolerances after thermal cycling and humidity. So, this concludes the chapter on embedded resistors and capacitors. For the next 10 minutes, I will take you through some very important issue that covers the entire course, that is the electronic systems packaging course. So, we have seen system level printed wiring board, we have seen what design is, what the green electronics are, what is reliability, electrical test, large area manufacturing, and a key component here is materials. So, we will briefly talk about materials here. The role of materials and processes in electronics packaging. It is diverse and crucial. Okay, the role of materials in packaging. Several important properties of materials are relevant to packaging, and we need to understand them, and we will also summarize some processes in packaging. If you look at the role of materials in microsystems packaging, there could be many areas. One could be the signal transmission from IC to IC. There we are worried about the electrical conductivity, okay, very important. Then we talk about electrical conductivity, that is from the battery to the IC, again through the interconnections. Then we talk about electromigration resistance and electrical conductivity in the electrical connection between IC and package. Then again various materials are used, you are worried about the melting points of these materials. Then we talk about moisture absorption, we have talked enough about this particular property. Hermeticity in packages, kind of metal caps that you are using to protect the die. Then we talk about die attached materials, especially in first level interconnect packaging, and then we talk about thermal issues, that is thermal conductivity is a key issue. So, heat sink materials also are very important. So, there are various materials that are used, various functions that can be defined, processes both that are in the first level packaging and the second level packaging. So, in the single chip, for example, we talk about protection, interconnection, heat dissipation. Materials that are used are plastics, epoxy and filters, ceramics and so on. Processes like compress, molding, tape casting, dry pressing and so on. Properties like TCE, permittivity, thermal conductivity, moisture absorption. In the IC assembly like tab, flip chip and wire bonding, we have seen various materials used: copper, aluminum, gold, polyamides, epoxy materials, Teflon and so on. There are different solder materials that we have seen, lead based, lead free, and then at the first level you have chromium, copper, gold, nickel being used. Then a lot of conductive adhesives we have seen are used today that are environmentally friendly. As far as the passives are concerned, there are various materials. Just now we have seen thick film hybrid circuits or thick film LTCC processes, materials like barium titanate, tantalum oxides, ferrites, ruthenium oxides, polymer thick films, carbon paste, conductive composites, etc. All of these are new materials that are being used, and we have just now seen various properties that are key to passives technology like TCC, leakage current, Q factor, temperature coefficient of resistance and so on. Now, finally, at the system level also they are very important, because when you talk about building system level printed wiring board, here again the key issue is what kind of organic substrate you can use, what kind of reliability issues you will get with processes like lamination, electroplating, photolithography, soldering processes, very key, and we have spent a lot of time on soldering processes. And there are various properties of materials that we have seen, like dielectric constant, loss, okay, elastic modulus, stress strain issues, CTE, moisture absorption, and so on. So, materials play a very key role in deciding the functionalities of products. Now, as we have seen in the previous slide, it could be in IC packaging, it could be in IC assembly, or in system level packaging. The electrical properties briefly that you must be aware of, which I want to summarize and give it to you in a nutshell, is conductivity. Okay, remember this equation, permittivity and loss tangent. You are talking about dielectric constant, capacitances of materials, ratio of capacitance of material to capacitance in vacuum, that is permittivity, very key property. Thermal conductivity, again it is the amount of heat transferred through a material per unit of time, denoted as heat flux, right, that we have seen. And area is here is very important, dt by dx is a temperature gradient we have seen. CTE, again it talks about dimensional change property of polymers and related material. Then mechanical properties we have seen, again Young's modulus, very key, because it again talks about the stress strain relationship and how these affect the materials that are being used in system level manufacture. Chemical properties, surface tension and wetting, especially in the case of solders, adhesion in the case of adhesives, conductive adhesives, and so on. All of these have been reviewed. Again, you should also know about thick film processes. We have seen ceramic, LTCC, screen printing, key issue, organics you have to be aware of. All the PWB processes use a wide variety of materials. Okay. There are innumerable materials that contribute to the reliability of the printed circuit board or printed wiring board. Then thin film processes, again for specific applications like PVD, CVD, physical solution based like spin coating, meniscus coating, dip coating, chemical solution based like sol gel, and not to forget photolithography process. Now, finally, the materials part of it and the processes in first level packaging and second level packaging are defining today the roadmaps in industry. Okay. New materials are being proposed, new materials are being tried by industry to generate roadmaps that are challenging for the industry, especially in the area of interconnects in the first level and second level. So, we are talking about today organic based interconnects, non-conductive adhesives play a key role when you mount these devices like tab or a flip chip. So, they definitely aid or play a key role in defining the interconnects on the system. Anisotropic conductives is growing, lot of challenges in anisotropic conductive adhesives and isotropic conductive adhesives. We have seen what they are when we talked about packages. Today the key is copper low K, okay, for highly reliable interconnects. So, the key is how do you use copper in conjunction with low K materials. Then again board materials that are green in nature, high TG, okay, and adaptable to PWB processing, and underfill materials if you are using chip on board technologies and so on, they are very key issues. Okay. So, when you are using flip chip for example, and then encapsulation materials if you are using chip on board technologies are also very key. So, that concludes the brief overview I wanted to give on materials and processes in electronic systems packaging. So, this concludes the module on embedded passives, embedded resistors, capacitors mainly, and then an overview on materials and processes in electronic systems packaging.